Okay, so welcome back to the lecture series of finite volume, and where we will continue our discussion where we left in the last lecture. So, piezo is kind of a combination of these two solver. So, what happened to simple C algorithm? Now, again as I said, this is a modified version of simple algorithm and it is derived by assuming the velocity correction at point C is some sort of an, so the velocity correction at C is some sort of an weighted average correction. I mean, taking care of that, some weighted average corrections of the neighboring elements. So, one mathematics becomes then B C prime, which was calculated as over all the cell A F V V F prime over F N B C A F B, which will get you summation of F over all the cell A F B V F, which will be V C prime F N B C A F B. Now, we use our H operator that we have done. So, this guy can be written as like F N B C A F B V A prime by A C V equals to V C prime summation of F over C A F B by A C V equals to H C V prime equals to V C prime H C 1, and then instead of neglecting the A C bar V prime term, so in simple what we have done that it neglects the term H C bar V prime. So, instead of now in this case we do not neglect this term, rather it is replaced. So, in this particular case this term is replaced by an equation which can be corrected as 1 plus H C 1 B C prime equals to minus D C V delta P prime C, which will lead to V C prime equals to minus D C V delta P prime C. So, now what it does, so from here one can use to derive the pressure correction equation, and the same result can be achieved by adding and subtracting the term of F N B C A F B B C from the momentum equation. So, you use this one in the momentum equation, and then if once you do that, the combining everything, it will lead to the A C V plus summation of F N B C A F B B C plus F N B C A F B V F minus V C equals to minus V C delta P C plus B C B, which in turn in a compact form one can write B C plus H C V minus B C equals to minus D C delta P C plus B C. So, this it can be used for the velocity corrections as B C prime equals to minus H C V prime minus B C prime minus D C V delta P prime C. So, the term, this term is dropped, which is equivalent to the approximation of the previous equation, a modified velocity correction is used driving the pressure correction. So, this is dropped and only this retain this term. So, this is a better estimate in simple C. The relaxation of the pressure becomes unnecessary and as compared to simple. So, in this case we may not require to be the relax the pressure, and the resultant velocity corrections will satisfy better the momentum equation, but consequently at higher convergence rate is obtained. So, the convergence rate is higher for this case. So, that is important. Now, the second another algorithm which sits in between is called the prime algorithm. Prime is stands for pressure implicit momentum explicit. So, the momentum equation solved explicitly, and the explicit treatment is justified by the mole contribution to the convergence. On the other hand, the pressure corrections pressure equation is solved implicitly. So, since the momentum equation is solved explicitly, one can get the new or intermediate velocity corrections like minus hc Vn minus dcv delta Pn, then C plus Vc B, and the velocity correction is applied to derive the pressure correction equation. So, the correction fields are now the correction fields one can obtain as Vc double star equals to Vc star plus Vc prime, and Pc star equals to Pc n plus Pc prime, and the corrected field, this will satisfy the equation Vc double star equals to minus Hc V double star minus dCV delta P star C plus Bcv, which is minus Hc V star plus V prime minus dCV delta P n plus P prime, which is C plus Vcb. Now, which will lead to the expression relating to the pressure and velocity field, like Vc prime equals to minus Hc V star minus Vn plus Hc V prime minus dCV delta Pc prime. So, this particular term, I mean, if you substitute in the continuity equation, which will get you back minus f NBC rho f df delta Pf dot Sf equals to minus summation f NBC m dot star f plus summation NBC rho f Hf V star minus Vn plus H bar V prime dot Sf. Now, the underlined term which is here, this can be neglected, or typically this is neglected. So, the term which is neglected in the prime, this underlined term can become smaller, and but then the term neglected in the simple. The simple algorithm, the neglected term was Hc V prime. So, this was not that smaller and can lead to the, I mean, slower convergence rate, but in this prime algorithm this term is quite smaller compared to that, and the neglection of that term does not have too much of difference, and it actually leads to better convergence. So, now using this simple C, and prime, the algorithm which actually works is a piezo algorithm. So, piezo algorithm is an interesting, it stands for again the in between of these simple and these things. And what happens in the piezo algorithm, that the which one neglected term in the simple algorithm like HCV prime, it is partially recovered in second character step. So, the piezo is essentially based on some sort of a predictor character kind of approach, and so what one can look at it, that because we have in the simple we have computed V prime and then neglected this guy, the continuity satisfying the V star star, the quantity V star star and pressure P star, so which were used to recalculate the coefficients of the momentum equation, and then to solve it explicitly. The new velocity field V star star is also used to calculate the M star 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 at the element faces using Riccio interpolation, and this guy HC V prime is also partially recovered, and the equation that does is that equals to Vc triple star plus Vc double prime, which is minus Hc V double star, this is double star, minus Dc V double star delta P star C plus Vc double prime, which will be minus Hc double star V star plus V prime minus Dc V double star delta P star C plus Vc double prime, which is minus Hc double star V star minus Hc double star V prime minus Dc V double star delta P star C plus Vc double prime, and this if you write Hc double star V star minus Dc V double star delta P star C minus Hc double star Hc double star minus Dc V delta P prime C plus Vc double prime. So, this equivalent to your Vc triple star. So, this will become Vc 1 triple star plus Vc double prime minus Hc double star Dc V delta P prime C. So, this term represent the portion of the Hc V prime which was neglected, and it is kind of in this algorithm partially recovered. And the second velocity correction, the second velocity correction that satisfies that Vc double prime equals to minus Hc double star V double prime minus Dc V double star delta P prime C. Now, using the Riccio interpolation between points, so interpolation between C and F, these are the cell neighbors, one can obtain the new pressure corrections equation, which is NBC rho f df delta Pf double prime dot Sf equals to minus f NBC m dot f star plus summation of f NBC rho f Hf bar V double prime dot Sf. So, this is again a term which are again this is neglected in the piezo also, and this corrector step may be replaced as many as times desired, so that you can lead to better convergence. So, if you look at how it works, so this actually kind of giving you the complete piezo algorithm, and one can also look at it any finite volume books, those are mentioned. It is a very standard algorithm. So, what happens, you first, this is at the t plus delta t time iteration. So, this is a physical iteration. So, outer loop as we have done in the simple, this is physical time integration. So, what you do at the time level t plus delta t, so you have all m dot f n. So, here m dot f n, v n, p n. So, these are all guess. So, this step is the guessing step. So, you guess everything, then you assemble and solve for momentum equation for all the star quantity. That means the first level of intermediate step where you calculate all the star quantity. Then you compute here the m dot f star using Ryo-Chow interpolation. You then after that at this step you collect everything and solve for pressure corrections. Once you are done, then obviously using the pressure correction, the m dot f star, v star and p n is obtained. So, these are use this, correct these things to get m dot f double star. So, at this step you finally get m dot f double star and v double star and p star, which is calculated based on these values which are corrected values using the p prime equations. Now, this portion of the algorithm, particularly this is exactly what we do in the simple algorithm. Now, here we again assemble everything and explicitly solve for the momentum, and here you solve for v triple star, because already at the second level of correction. So, what happens is that it goes in multi-level iteration. So, the first level you do simple kind of algorithm, and initially you started with the guess value. Once you get a corrected value, you use that for the next level of algorithm where you obtain v star, v double star. Then again you calculate the m dot f triple star using Ryo-Chow interpolation. Then you get pressure corrections equation, here you corrections for p double prime, and then after that at this step what you do, this step you actually get the corrections field m dot f triple star, v triple star and p star, and these correction fields are used to calculate m dot f fourth star, v fourth star and p double star. So, these are used. Now, if the number of corrector step exceeded, if it is yes then you move, if it is no then you actually assign those value here to the double star value and repeat this process. So, this is the part of prime algorithm, and this prime algorithm is repeated. But if that is exceeded, then you do at this step you get m dot f n equals to m dot f 4 star, v n equals to v 4 star and p n equals to p double star. So, you assign that, if it is converged you move ahead, if it is not you go back and repeat this test. So, again you compile simpler piezo algorithm. If it is converged you update these things for the next t plus delta t iteration, advance in time, again the time limit exceeded stop, or you go back and do the physical iteration. So, it does twice kind of or 2 times of the iteration in the process. And now that is why piezo is provide better stability, better convergence, and if you have a slightly non-orthogonal skewed grid and those kind of cases, actually piezo works better than simple algorithm or simple C algorithm. So that is why it is preferred, and lot of the CFD codes actually is based on piezo. They provide a better stability and better convergence. Now moving ahead, we have used under relaxation factor. So now one can look at the optimum under relaxation factor for V and pressure corrections. So what one can see, if you recall the velocity corrections, how we do that? We do that minus dc into del p c, and calculating the pressure field, we use some sort of an under relaxation in the velocity corrections, and we wrote in this fashion, where Vc prime equals to minus Hc V prime lambda dc delta p prime c. So that is how we written. And now if you equate these two guys or these two equations, one can write minus dc delta p prime equals to minus Hc V prime minus lambda, which will provide lambda p equals to this, or so that gives an, so the simple C algorithm eliminated the need to under relaxation pressure corrections and result in an optimum acceleration rate. So therefore, using an approximation introduced with the simple C, the velocity corrections at C can be written and weighted average like this. So this is done in simple C, and this is the corrections for lambda for p prime. So the pressure correction equation, this kind of correction factor. Now when you move ahead from the simple to simple C, the kind of corrections was eliminated and the velocity corrections can be estimated like this. This already we have seen. So there is nothing new here that we are writing. So if you go back to your expression for the simple C or simple algorithm, you will find this expression, and then the coefficients can be written in this fashion, invoking the under relaxation factor. So if you simplify that, you will get this, and so the role of under relaxation would limit to this. Now if you substitute this equation in the velocity corrections approximation here, if you use this one here, then you get Vc prime equals to a b by lambda, from where you get lambda p equals to 1 minus lambda b. So what people have seen that simple algorithm with its under relaxation factor satisfying this equation provides to similar to that kind of simple C kind of algorithm. So that's an optimum lambda calculation for simple algorithm which can behave like an simple C algorithm. Now one more important thing which one can discuss is the Ryo-Chow interpolation and the treatment of the various terms in the Ryo-Chow interpolation. So first one can look at the under relaxation term. Now the under relaxation term in the momentum equation, this is how one has written the momentum equation, and the under relaxation term written like that. So if you do some sort of an algebra, this is for momentum equation and velocity corrections, you get back this equation, which is again we have looked at while looking at the momentum corrections equation, and then the Ryo-Chow interpolation should be written in this fashion, and this particular term one can express that contribution from the element C and the contribution from element F. So finally this actually leads to a some sort of an calculations of the phase variable which is written as Vf. So all this algebra you can carry out because this starts with the momentum equation. The important point here is that you get back the surface value which is a average surface value, then there is a delta p f and delta p gradient, and then 1 minus lambda. So this is how when you use under relaxation the Ryo-Chow interpolation actually gets modified. Similarly, same equations can get modified for the temporal discretization. So when you have written the temporal, here this stands for t minus delta t or previous time steps, and nothing stands for t or the present time step. So, this is my momentum equation with all the discretized form. Then you write at the phase, this is the modified, and the phase value can be average like that, and once you expand this, finally you get, this is an important calculation for the transient term, how the phase value one can treat, and that case you get phase value minus this and you use these things. So, also one can do the treatment of the under relaxation body force term, and body force term, if you do the treatment, so you can actually get, so and then just let us look at one important thing for the interpolations for all combined effects, which takes care of the under relaxation term, transient term, and it also takes care of the body force term. So, then the surface vector Vf is a average dFb delta Pf minus delta Pf bar dFb, this will the term which will come due to body force term, and then these contributions are there. So, this is how one can look at the interpolation scheme in this kind of system. Now, having said that, that pretty much actually takes care of the discussion on the incompressible flow. Now, we will extend the discussion, similar discussion where you can also obtain the pressure corrections equation or all these things for compressible cases. Now, there is a important difference between compressible case where it is like that, its density is no more constant and Mach number is quite high or greater than 1. So, that is where the compressibility effect starts acting, and once that is happening, you cannot actually assume the density to be constant, rather density to be approximated using ideal gas law. So, that is where the now in the compressible flow solver there are two types of approach. One can have density based algorithm and one can have pressure based algorithm, and what we are discussing so far all are pressure based algorithm, and when deriving the equation for the incompressible case we did not bother about density too much, though we retain the density in the term. So, similar algorithm we can directly extend for the compressible cases. Now, the other thing is that density based algorithm is not the scope of this particular lecture. So, one can talk about that in details in a separate lecture, because it has different kind of issues altogether. So, right now we will concentrate on pressure based algorithm and can see how we can achieve. Now, these are the set of equation. This is your continuity equation, this is your momentum equation, this is your energy equation. Now, when you, and one more equation which will be required is the ideal gas law, P equals to rho RT, which will get you calculate the rho by P by RT. So, top of this all you need this equation where the pressure and density can be calculated and connected with the temperature. So, in compressible case, when we are talking about now, if you see the difference between incompressible case, we did not really bother about the energy equation, but when you come down to compressible case, so these are very standard equation, and any textbook on fluid mechanics or compressible flow you can find this equation. So, there is no point going into the details of this discussion. So, and rather we have done detailed discussion in our initial lectures when we derived our governing equations. Now, these are connected. So, let us look at a element C, which is our standard element. You have all these 6 faces and these are fluxes or flux vector, and then if you actually take a volume integral of the diffusion term, which will convert to a surface integral like this, which we have already seen, and delta dot mu f will be mu f into this, and any flux gradient calculation can be contributed one is the GC and GF. GC and GF are the geometric coefficients which we have used earlier. Now, how would you derive actually pressure corrections equation? So, first equation that will start with P equals to rho r T, and if you expand rho using some sort of an use Taylor series to expand rho, then you write a rho equals to rho plus del rho by del P. So, it is rho star plus rho prime. So, rho prime becomes Cp like this. So, similarly you have the corrections of the velocity and pressure field. So, the pressure, previous pressure plus correction, density, velocity, mass flow rate. When we looked at the incompressible case, we did not bother to look at the corrections of the density. Now, we need both corrections of all the density and all this. Then if you put this in the semi discretized equation, this is how it looks like, where mass flow rate would be rho f star plus rho f prime, Bf star plus Bf prime, and which will boils down to two quantity. So, this is the second correction term is usually this is neglected, and then we obtain the detailed correction term. Now, we will stop here today and we will take from here in the follow up lectures. Thank you.